I'll talk now about some of the other technologies we've been working on, just to give you a sense of the breadth of our center. This is a composite arch bridge system that we've developed that was recently recognized by the White House a few years ago as a major instrument of change. It's really the Innovation Award. And this technology is now being used by the Advanced Infrastructure Technologies. It's a new company. It's been spun off and has licensed the technology. And they've built over 24 bridges using this concept. We've also worked on another bridge technology. It's a composite concrete hybrid bridge. It's actually the longest composite bridge in the world. We were involved in that project. It's over 540 feet long and 32 feet wide. It was opened in 2011. We also worked on managing and designing the first all-composite hull for the U.S. Navy with another spin-off company called Hushin Defense Composites. This is called the Mako. The boat itself was intended to replace an aluminum version of the hull that, because of the aluminum structure, actually vibrated and caused injuries to the occupants of the vessel, which was the Navy SEALs, the Navy SEALs vessel. And this boat goes extremely fast, and the wave slamming forces was causing injuries such as dental fractures and spinal injuries to the Navy SEALs. So the idea was to use a composite hull, which is made of shock-absorbing materials. So this is that hull. So it was built and during its maiden voyage down in Boothbay area here in Maine. This is during some of the initial sea trials of the vessel. And doing some of the extreme maneuvers. This is a top 180-degree turn at full speed. That's one of the maneuvers that was required to demonstrate. In the area of wind, we are one of 3 facilities in the United States that does wind blade research and structural testing. This is an aerial shot of our laboratory. You can see here. This is a 56-meter long, so about 160 foot long blade that was brought into our lab and was tested for commercial entity. So this blade is brought right in here and mounted onto a wall, and we simulate the equivalent of 20 years of wind loading to ensure that the structure meets all the appropriate requirements and standards, engineering standards. So this lab has been open now since 2009, and this is a video of our blade testing. This is the fatigue type loading. To give you a sense, this tip of the blade is moving, plus or minus by 15 feet. So it's a very dramatic loading that we do, very large structural scale testing going on in our laboratory. In terms of offshore wind, this is a video of our floating technology, which was deployed back in 2013. We deployed the first floating offshore wind turbine in the U.S. It was the first grid-connected unit. The goal of that project was to study how these units survive extreme waves and winds. So this unit was deployed offshore, Castine, Maine, and in a site that produced scale wind and waves. The unit is 1/8 scale itself, and that was the whole purpose of the experiment, was to show how it would survive these types of environments. Floating wind is a newer concept that's being researched by a number of countries around the world. There's already offshore wind turbines in Europe, but they're all fixed bottom. And only recently, in the last, say, 10 years or so, has floating wind been looked at. Why floating wind? Floating wind is, the reason why you go in that direction is because the water depths drop off in a lot of regions of the world, including the US and Japan and other parts of the world. The fixed bottom technologies just really don't make sense at those depths economically. So these floating technologies, the idea is that you can capture more of the wind resource. You also can build the hulls completely on land and minimize offshore construction. So that's what we're demonstrating here in this video. This unit was tugged out from a port, it was constructed on land, and then towed out and hooked up to some mooring.